Hi, welcome to this short video where we'll configure and tune a drive using the latest version of Connect, the software tool from Control Techniques for drive setup. The demonstration is given using a Unidrive M700, however, the steps to set up a Digitax HD are the same. So in terms of the hardware and connections, we've got a laptop. That laptop has Control Techniques Connect software loaded into it. There's then an Ethernet connection through from the laptop through to an Ethernet port on the product. Product in this case is Unidrive M700. In terms of loading, we've got a Control Techniques Dynamics motor with a flywheel on the end, so that when we come to the tuning part of the process, so tuning up the speed loop, we've got something to simulate realistic load dynamics. So before we actually get into the demonstration, I just want to point out that there's a getting started guide that shows how to do all of the steps that we're going to see in the video and how to connect up with other different communication protocols. So here is the guide, and what you can see down the left here is we leave the PDFs that we create with the bookmarks open, and you can see that here is the section that we would follow to get connected over Ethernet, which is what we're going to use in this demonstration, and then we're going to follow on with section 3, configure the drive using Connect. Okay. However, if you wanted to connect via Bluetooth because you've got a KI Keypad Plus, or you've got a serial lead and you want to get connected using that mechanism because you've got for example, a Unidrive M701 or a Digitax HD M751, we've got a section here to cover how to get the basics connected using that. However, once you've actually established the connection, essentially all of them use the same steps in order to configure and tune the drive. So let's get started. So what I'm going to do is I'm going to fire up Connect. Here we go. You can see it's a brand new splash screen for version 3, and you can also see a brand new desktop icon. So in order to get connected to the product, we need to click New Project from Network Scan. So I'm going to click that. And then the three that would probably mostly be relevant for this video: Scan Bluetooth, Scan Serial, Scan Ethernet, or if you're unsure what you've got connected to your drive, you can choose Scan All Networks. There are other videos in the series that will show you how to connect via TwinCat ADS or via EOE, such as if you're making a code assist type application. So I'm going to click Scan Ethernet Network. And bear in mind, I've got a completely defaulted drive, so it doesn't have any IP addresses set or anything like that, and the drive itself is in open loop. So there we go. You can see that it's gone and found my device, but you can also see that it hasn't got an IP address set. So let's go and configure that. So I'm going to hit configure, and I think I'll just leave it at that, the default that it's come up with. So my IP address is 192.168.1.1, and I'm going to click apply. So what this is going to do, this is going to go and update the IP address of the product automatically and save it in there. Excellent. So now we're ready to get going with our project. I'm just going to name it. So I'm going to say get going connect, and I'm going to select new project with selected drive. And there we go. So for previous users, you can see that this is an entirely new desktop space, all new icons, all new styling. However, everything that you were used to using before in the previous style, so the previous style was more like a kind of Windows desktop icon kind of style. Okay, so you'd have had an individual fairly large icon spread around a dashboard that you could then click and select whatever it was that you're attempting to do. In version 3 Connect, we've collated all of those things, so everything that you would have wanted before is now held within the project menu. So for example, if you wanted to, I don't know, use the oscilloscope, you can find that in this menu. If you want to go and have a look at the terminal overview to see what's going on with the terminals, it's there. If you want to look at parameter reference guides, if you want to look at the parameter listings, they're all here in this menu. Okay. But for the purposes of what we're trying to do for this particular video, I'm going to crack on with the drive configuration. And what you'll notice to begin with is that when you open a new project, the drive is brought online directly. So that means that any changes that you make here are directly affecting the product. You're directly configuring the product. Second thing that you want to notice is that we have a nice status bar here at the bottom that tells you basic information that's going on with the product. Okay, so this here tells you the drive's display status, so if it's inhibited, if it's in stop, if it's in run, if it's tripped, if it's in alarm, etc. If it's tripped, what you'll actually see here is some information about that trip, and you'll also have the ability to reset. Okay, plus you've got some basic metrics here. You know, have you hit the current limit? Is it at 0 speed? What does the DC bus voltage measure? You know, what reference have you got, etc. Okay, current magnitude. So all useful stuff, all there all of the time, so you've got some kind of gauge on what's going on with your product. So next thing, we now give users for Unidrive M and Digitax HD a guided setup. So rather than the kind of V2 arrangement for Connect where you had individual tools for setting up certain aspects, but as a user you had to know what all of those tools did and in which order to use them, we've now got a guided setup. So you can see each of these individual stops along the guided setup process is something that you need to set up in order to get to the end goal, finalize it, and your drive is operating and running. So first thing that we're interested in doing, because I've got a servo motor, is that the operating mode for my particular drive is open loop. That's how Unidrive M comes out of the box, but my motor is servo. As you can see from this table, really what we need is RFC S mode. S for synchronous machine. Permanent magnet motors such as servo motors are used in RFCS mode. So I'm going to go ahead and select that. So there we go. The driver's just reconfigured itself into servo mode, and what we can see is that we've got no encoder found, and that's simply because we've changed the operating mode from open loop, where it doesn't have an encoder, to servo mode, where it does have an encoder, and we just need to go and configure that, and then this will become reset. But what you can see is that we've got some suggested actions for things that you could go to correct that, and you've also got the ability to reset the drive. Bear in mind you can reset from this control, and you can also reset from the control in the toolbar. So let's move to that next step. As you can see, you can move to the next step either by clicking next and back here, or as I tend to do, to be honest with you, I tend to just click the step that I'm actually interested in activating. So you've got the standard motor setup here, all of the general motor nameplate stuff. You can also search. So for example, if you've got Control Techniques Dynamics motor, so this is one that I happen to know, 067 EDA. This is a list of motors that are on the Unidrive M demo case. However, the particular motor that I'm using for this demo is a slightly older one, and I'm using it just because it's got some inertia on the end so that we can tune to it. So I'm just going to go and enter these things in manually. So for my motor, it's a 6000 RPM motor, it's 6 pole, it's 28 volts per 1000 RPM, and its KT is 0.47. Now just a quick word on torque per amp. If you've got a servo motor, it's quite important to enter the torque per amp. Okay, if the rating label on your particular motor doesn't have torque per amp listed, you can derive the torque per amp by dividing the motor rated torque into the motor rated current to get an approximate value that would be good enough for the purposes of what we're trying to achieve. And what this does for you is that when you go and measure the motor and load inertia, it allows single slider tuning. So instead of having to individually manipulate proportional gain and integral gain and get the balance between those two factors right, if you learn the motor inertia, then we can effectively set those factors up for you where the left side of the slider is less tuned and the right side of the slider is more tuned. So it's very simple to get good performance from the motor without actually knowing an awful lot about tuning. So I can't recommend enough, please set this value. Next thing that we're going to do is we're going to go set up the encoder, and you can see there are a couple of tabs here. Okay, one for the encoder interface, which is going to be for the motor, that's the one that we're going to set up, or if you've got an application that has a second encoder interface, you can click this tab and have a look at that. For the purposes of what we're doing though, I'm just going to go and set up the encoder. So for my particular motor, I've got a sine cos hyperface, and I'm going to set it to 8 volts because these particular encoders are 8 volt encoders. And what you can see is that the encoder trip that we previously had has now been reset because we've gone and configured the encoder properly. So that's as much as we need to do on this step. Let's move to the next one. So brake control. So this has two aspects, I suppose. One is for electrical braking. So this is managing energy that comes back into the DC bus if you slow down very rapidly. And I'll show it. We're not going to use it in this case because I haven't got a braking resistor. The amount of inertia that I've got in my load isn't sufficient to require it. But if you've got a high inertia load and you're decelerating very rapidly, your DC bus will increase as you brake, and you've got to do something with that energy that's flowing back into the drive when you brake. So one way that you can do that is with a braking resistor, and obviously that braking resistor requires some protection. You can't just keep dumping energy into that resistor, eventually you'd burn it out. So your primary protection is normally some kind of thermal device that would cut out power going to that resistor, actually, physically fitted to the resistor itself. Secondary protection is this that you can go and configure in the drive. So you need to tell the protection system how many ohms the resistor is, what the power rating of the resistor is, and what the thermal time constant of that resistor is, so we understand how much power can be dumped into that resistor over time. So I'm going to say no because I don't need that for my particular application, and I'll just show you the mechanical brake control setup. So for the mechanical brake controller, if you say yes, you get this selector. Okay, the only one that you really need to set up is this one, which says to the solenoid or relay or whatever it is that's in control of releasing the brake, which terminal from the drive are you going to use in order to control it. So it can be classic digital outputs, or it can be a relay output if you want volt-free contacts in order to control that solenoid. Next thing that you'll need to do is to set up your post-brake release delay and brake apply delay. So the purpose of these are system weights to allow the mechanical brake to physically release or physically apply. Usually that's somewhere in the order of, 200 milliseconds to 1 second. The default is 1 second, but if you want to make your machine start as quickly as possible, you might want to reduce this to the actual time for your brake to release. And you can optimize it even further with this brake released indicator input, which will effectively bypass the brake release delay because you have a switched input that says, hey, my brake has become released. However, for this application, I'm just showing it for completeness. So next thing that we've got is our references section. So this is how you're actually, during operational use of the drive, this is how you're actually going to supply your reference. Okay, so there's a few selections here. For me, I'm just going to choose preset reference. And there we go. And there's a few things here to be set up. Okay, so we can choose what the maximum reference clamp is. For me, I'm quite happy at that staying at 3000 RPM for this rig. I could take it all the way up to 6000 RPM, which is the rated speed of the motor, but I think for what I'm trying to achieve here, 3000 is perfectly fine. You can also set the minimum reference clamp, so if you've got a requirement that your motor never goes below a certain speed, you can set this. For most applications though, I'd say it's probably going to be 0. You can then set your acceleration rate, deceleration rate, or deceleration time rather, so in seconds per 1000 RPM, and then you can choose whether or not these units are seconds per 1000 RPM or whether they are seconds per maximum reference clamp, and this is quite a popular choice, seconds to reach your maximum speed. I'll leave that off for now. You've also got choosing whether you have SRAMP in there, so you can notch it up individually, or you can, I'd say 50%, there you go. And what you can see down here is that the graphs that we've got that kind of represent what's going on with our jogging reference and what's going on with our main reference, all modified to give you some kind of visual representation of what it is that you're trying to achieve. You've also got I/O selectors, so by default obviously there are terminals available for running forward, running in reverse, jogging forwards. There isn't one for jogging reverse, but we could assign that if we wanted to. You know, we could assign one of these other terminals to become jogging reverse if we wanted to. So, for example, I could make it terminal 24. Okay. So that's about as much as I think we need to kind of cover here. Let's move on to our limits. So if you've got a linear axis or a rotary axis that happens to have limits, this is where you would go ahead and wire up your limit switches. So you've got a forward limit switch, a reverse limit switch. Same as before, you've got a selector of all of the relevant terminals on the drive that you might want to select in order to input a forward limit switch and to input a reverse limit switch. Okay. So at that point, we've basically set up all of the main properties that we need to get a basic system going, and I'm going to choose to save those parameters in the drive. Next, we need to do an auto-tune. So this is to work out the phase offset between the magnets in the motor and the alignment of our absolute encoder. So ahead of time, and I'll just show this in the nice new terminal overview, what I've got, and the minimum that you need in order to be able to progress beyond this point, is I've got a switch that connects between terminal 22 and terminal 31, which is the drive enable input. Bear in mind that not all drives use terminal 22 into terminal 31, and some of the drives in the Unidrive M range and Digitax HD range have more than one safe talk-off input that allows the drive to be enabled and disabled. However, for this drive, it's a switch between terminal 22 and terminal 31. So let's close that. So I'm going to select Start Auto-Tune, and then I'm going to enable the product with my switch. And there we go. And I'll just bring on the camera feed. You can see this is my particular motor just turning during the auto-tune. When you're using a servo motor, it's best to use the slow rotating auto-tune if you can. So we'll wait for that to finish. That usually takes in the order of, I don't know, 20-30 seconds, something like that. There we go. Finished. Okay, so I'm now going to disable that. And you can see here are all the tuned values. So it's tuned up the current controller gain. It's given us a phase angle of 0, which is typical of Control Techniques Dynamics motors. So we can now move on to the next step. So the motor and load inertia. So the reason we're doing this is to make it so that our tuning in a later step is much easier. So I'm going to select, I think I might increase the mechanical load level a little bit to 5% just to make sure that I don't have to repeat the test. And I'm going to select Start Auto-Tune. So I'm now going to enable it, same as I did before. And what you'll see is that the motor is sort of oscillating backwards and forwards. And what's happening is, as it's applying all of these different test frequencies, we're slowly understanding how much movement that we're getting, or how much acceleration that we're getting from the motor for a given frequency. And from that, we can infer what the motor load and inertia is. So again, takes 20 or so seconds. There we go, that's finished. So it's telling us to remove 24 volts to complete the test. So I've done that. And there we go. Here's the inertia of my motor. So we're ready to move on to the next step, which is the performance tuning. Now, I'm just going to move that over a little bit, just so it's not fouling some of the things. So there's a fair bit to cover here. This is a brand new view. Previously, if you were doing tuning, you would have to have done something like start CT scope, and you'd have probably been swapping between Connect and the scope view in order to see changes that you had made, and the effect on the performance, okay, using the scoping tool. Now we've got a one-stop shop tool that does everything for you, and I'm just going to briefly cover the aspects of this. There'll be a more detailed video later that will cover, how to use all of this in detail, but for the purposes of tuning, there are really only a few controls that you need, because essentially we set the scope up for you from default, so all you've really got to do is press start, okay? But I'll cover these controls. So here we've got top left, we've got the scope control. So this starts, stops, and sets up the time base for the scope, how much data per division. So Next thing that we've got are our channel selectors. So you've got 8 analog channels, 8 digital channels. And then, as you can see, we've gone and set these up for values that we think would be appropriate to you whilst you're doing your tuning. Okay, so we've got DC bus voltage in here as well. We've got percentage load in here. Those aren't checked by default because for tuning, honestly, you don't normally need them unless it's a very arduous application. Okay, so what we've got on here, so here's the scoping view. We've got speed error, position error if you're closing the position loop, whether the drive has gone into current limit, and then we've got our speed reference and our speed feedback. So all the important values that you need in order to be able to tune. So the next thing, which is new in this version of Connect, are the test move controls. And I'm going to go ahead and enable them. You'll see how these work just by use. So I'm going to say take drive control. Okay. So what we're doing here is now the PC tool, so Connect itself, has taken control of the drive. So the only thing that you need to be able to do is apply 24 volts to the STO input to enable it, and it tells you to do this here. So I'm going to go and close my switch, and there we go. So we're now ready to begin, doing some movement. And you can see each of these buttons has a different function. So we've got jog backwards, automatically run backwards, automatically run forwards, jog forwards, and then the stop function. So if you're using any of the automatic, run backwards, run forwards features, this is how you would end up stopping it. So pretty useful stuff. So the first thing that you want to do when you're setting up your application is actually just find out whether it's basically turning in the right direction. So if you jog forward, is the motor actually turning forward from the perspective of your application? So I'm going to go and click that. You can use F keys if you want. I'm going to do it using the mouse so you can see what I'm doing. So there we go. You can see from the video feed that's now jogging forwards. You see there's a little delay in the video feed, but you can see it working. So what I'm going to do is I'm going to take this down to a slightly slower speed. So all of the profiling that you'll do with these controls are controlled from the profile settings tab. So there we go. I've gone and changed this to 50. If I start it now, you can see it's much slower. So you've got full ability to control all of that. You've also got the ability to see from this profile what it is that the profile is going to look like. Okay, so what I'm going to do next is I'm going to start an automatic profile so that we can begin to tune against it. So I'm going to select run forwards here, which you can access via F3. And what this is doing is it's running forwards and then backwards. I'm going to start the oscilloscope so that you can see this. There we go. So I'll just wait for that to refresh the whole screen, and then I'm going to stop just to describe this. So what you can see when we're accelerating, when we reach our target speed, and indeed when we reach 0 speed, you can see that by default we're able to kind of achieve our speed, but there's a bit of overshoot in there, and that's not desirable. You can also see it from the speed error that there's a bit of oscillation there, okay? And that's all basically caused because there's a reasonable inertia on the end of the motor and we haven't actually begun to tune it up yet, okay? So the next step, I'll just start that again, is we select the tuning tab, okay? And you can, if you want to, manually try to change all of these, but because we've taken our motor inertia value here, actually we can just select bandwidth mode. And watch what happens when I select this. Okay, so what's happened, we're in bandwidth mode, and the higher the bandwidth, the stiffer the response that you'll get. The lower the bandwidth, the more dampened the response will be, and I'll show that. So if I drag this slider down to, I don't know, kind of 9, what you can see is that firstly, we've got a little bit of overshoot here. It's not a very tight response. You can see that the speed error has peaks in it, but if you observe the P and I terms here, you can see that the balance between the P and I gains has already been calculated for you, which is a nice property. You haven't got to work that out or try to guess it or try to estimate it. It just works it out for you. So if I raise this slider, up to the sort of 70 to 100 hertz region, because that's usually where most applications are in, pretty good tune, you can see that again it's raised both of these in proportion. It's nice and easy, it's a single slider, and you can see that there is basically no overshoot. So you can tell that for this particular profile, the profile that we've selected here, the drive is as well tuned as it's going to be. Now obviously when you're doing this, your particular machine might have different requirements. You might need a faster acceleration rate with this than this one that I've chosen, and therefore your tuning requirements will be somewhat different. But the key thing is, if you sample the motor and load inertia and then select bandwidth mode, it's very, very easy to sort of set up and tune the motor. So other tools that you've got here for kind of setting up and tuning your motor, you've got your current limit. So it could be for your application that 175% isn't enough. It could be your motor drive has been rated to give 200%, for example, and that's actually what you need. Here is where you could go about setting that up and optimize it for your particular application. If you're doing a hoisting application, for example, when you ramp your application down, you might want to hold 0 speed. Here's where you can change that. And you can also, if you disable the drive, change the motor direction. So if when you've jogged, you found that your motor is basically not turning the right direction, without having to change any wiring, you can change the direction, which is quite helpful. So last of all, and where I'm probably going to make a little bit of a change, because my particular driver motor has been rated for 16 kilohertz operation, so I can go and select that. Here is all of the things that you can change that might affect motor noise. So for me, I can hear the 6 kilohertz switching frequency coming from my motor. I don't want to hear that. I'm going to push it up to 16 kilohertz. Then all of a sudden, now my motor's nice and quiet. Okay. Other things that might help you here are current loop filter time constant. If you're doing an application that isn't closing the position loop, it might benefit you to increase this up to sort of 2 to 4 milliseconds. If you're doing a positioning application, one where you're closing the position loop, you might want to keep this around 1. So I think that's as much as we need to show for tuning. You can see that it was pretty quick and easy. I'm now going to disable the product. I'm going to release drive control and stop the scope. Last of all, you want to be able to preserve your application, so I'm going to choose to save the parameters in the drive, so all of that tuning that we've just done is now preserved in the product. Next thing that you want to do is make a backup parameter file. So by default, you end up with a parameter file. It talks about the drive's name, it gives a date and time that the parameter file was created, but you can append that to say initial tuning, for example, and then choose to save that. Okay, so if I close this and close the motor view, if you want to come and restore that, you could come here, parameter file, and if I expand that, you can see here is our parameter file. You can click on that and then you can then restore it by selecting download. And there we go. That's all of the basic steps that you require to go and set up a Unidrive M and a Digitax HD. Bear in mind the steps that you've seen here will be identical. Okay, hope you found that interesting. Thanks for watching.